Okay, shall we start the session, sir?
Yes,
Okay,
this is
okay.
I
So,
have to share my screen first.
okay, so shall I start the introduction?
Wait a second. Yes.
Okay,
Give me a moment. I have to share my screen first, right?
okay.
And then after that, please start this
Yeah,
introduction and then we'll start. Okay, finish?
yeah, okay, sir. So, okay, I will start the
Oh,
session, okay? Okay,
okay,
great.
fine.
So, good morning, everyone, and welcome to the Mastering Up International Conference Series 2025 to 2026. Today's theme is quantum computing and future technologies. Super exciting stuff again. And big cheers to Dr. Ram Soorat and all our amazing participants. You all rock. Let's keep it chill, interactive, and fun. And grab your coffee and let's dive in. Ladies and gentlemen, and dear friends, it's an absolute delight to welcome you all to this exciting session on getting started with quantum computing from qubits to circuits. Whether you are a tech enthusiast, a curious learner, or someone just diving into the world of quantum, you are in for a fun and insightful ride. Today, we are going to take a fascinating journey through the basics of quantum computing. So, don't worry if the terms sound complicated right now, we will break it all down together, step by step. Think of this as a conversation, is not a lecture. So feel free to ask your questions, share thoughts, or even just sit back and soak it all in. Let's get inspired before we begin. The future belongs to those who learn more skills and combine them in creative ways. Let this be your moment to explore question and get one step closer to the future of tech. So let's get started. Before we begin Dr. Ram's session, I would like to take a moment to introduce him. So, alright, everyone, I hope you are ready for some serious inspiration because today we have the absolute honor of welcoming a truly remarkable human being to this session. So, please join me in giving a warm virtual round of applause to Dr. Ram Soorat, Assistant Professor at Wagzan University, Hyderabad, India. Dr. Soorat is a rock star in the world of quantum optics with a PhD from the University of Hyderabad and a career that bridges both academic brilliance and hands on innovation. He's worked on everything from quantum cryptography and QKD to quantum error correction and circuit design. He is not just a researcher, he is also been chief scientist at AIFI Technologies in Abu Dhabi, and he brings a rare mix of deep technical knowledge and real world application. Whether it's publishing in top journals, presenting globally, or mentoring the next generation of physicists, he's done it all. Let's kick things off with a quote that perfectly fits today's energy. Success is not just about what you know, but how boldly you applied it in the real world. We were beyond excited to learn from Dr. Surat's journey, insights, and passion for quantum tech. And before we dive into today's session, I would like to take just a moment to introduce you to something that's close to our hearts, Thames Tech Solutions, a proud Swiss venture that's changing the way we see and use technology. At Thames, we stand by three simple but powerful values: innovation, excellence, and affordability. Whether it's cutting edge engineering or next gen scientific tools, we believe everyone should have access to transformative tech. As the visionary Steve Jobs once said, innovation distinguishes between a leader and a follower, and at times we choose to lead with purpose. From digital marketing and web design to AI powered tools, server management, and mobile app development, our work spans across the industries like aerospace, medical applications, energy, and more. We don't believe in one size fits all. We believe in tailored solutions that help Businesses thrive in a world that's constantly evolving. As Albert Einstein wisely said, strive not to be a success, but rather to be of value. That's our mission. To add real value through strategy, technology, and a mindset focused on progress. But what makes us most proud is not just our business, it's our impact. With our initiative, Mastering Up, we are focused on empowering the next generation by equipping students, especially from rural and underrepresented areas, with real world skills for real world success. Because, as Nelson Mandela said, education is the most powerful weapon which you can use to change the world. So, today, as we begin this session, let's not just learn, let's imagine, build, and shape a brighter tomorrow together. The future starts now. So, at the end, I would like to introduce to the motto of Dr. Ram Soorat: Think quantum, act bold, shaping the future one qubit at a time. So I would like to hand over the session to Dr. Ram, and also thanks a lot for joining us today, and over to you, sir.
Um, am I audible?
Yeah, yes, sir.
Okay. Thank you, Sunati, for this nice introduction. I really appreciate that. So I'm going to start my talk as I am Nelson, that getting started with quantum computing, and I'm going to start from very scratch. This if if you don't know about quantum, what is quantum? If you are hearing first time, even though no need to worry, I'm going to dig out a lot of information from basic, and after this session definitely you are going to understand something. So this is start from qubit to quantum circuit. So I will discuss about this qubit, what is qubit, and why this is different from classical bit and all, and then we'll see the hands-on session also. I will I'll make one circuit and IBM quantum computer, and we will you can see that how this is working. So as you know about me, here is my telephone number, mobile number, and this is my email ID. So if you, after this talk, if you feel something to discuss or want to collaborate with me about work and all, please feel free to write to me or text me here. And okay, so I'm just going to start about my topic. So this picture, I think several people have seen who is working with quantum. This is when the Google talked about the supremacy and all. So here in this talk, I'm going to talk about this quantum computing from representation of qubit on block sphere, and then I'll discuss about what is gate, how this is different from classical gate. And in gate, I'm going to target these three gates, especially which is very well known in this quantum computing, and this is very much useful as Hadamard gate, Pauli gate, and CNAT gate, and Toffoli gate. We used to call this Toffoli gate as a CNAT gate. After this, I'll discuss about what is quantum entanglement, how this is going to work, how we are going to write mathematically. And then quantum teleportation, we'll discuss about this quantum teleportation, how we can transmit a quantum state from one place to other place. We'll see the quantum circuit and on IBM Google computer, and it's a kind of live demo. And then, of course, regarding that, how we are going to set up this environment and writing simple quantum circuit, and then hands-on session. And after that, I will go for question and answer. If you have any question, we'll discuss about this, of course. And yeah, so this is what I'm going to cover in this 1 hour session. So the first question is that why quantum? Because we are very much familiar with this classical computers, and now I'm using this classical computer and interacting with you. Whatever task is there, we can do it easily. So why this quantum computer comes in the picture? Why do we need this quantum computer? So for this one, the thing is that when we are talking about macroscopic, it's easy for us to do all the sort of information whatever we are looking for. But when we are going to macroscopic level, it's going to fail. Means when classical computer is failed to do some task, then quantum computer comes in the picture. So this is something which is different from classical computers. Classical computer uses only 0 and 1, it's a logical bit, 0 and 1, or we can say on and off. So this classical computer used to understand only 0 and 1, and of course this is this slow down also because this is transition limit, and struggle with complex optimization problems, simulating quantum system and factoring large number like RF encryption, etc. So these are the problem actually this classical computer often face. So for that quantum computing comes in the picture, and the advantage of this is that we can write in terms of this qubit in terms of superposition, and this superposition has multiple parts. It has the n-dimensional information that we can write, and we'll discuss about this in detail in coming slides. And then of course entanglement is there, which enables correlated results without direct interaction. And then quantum parallelism, which is to speed the computing problem. And then nowadays there is several companies which is involved and doing a lot of quantum stuff, and like cryptography. These are the area where, of course, it's not limited, but you can explore in even many more area. I have worked on this quantum cryptography, and here in cryptography, solo algorithm, certain RSA, but enables safe encryption. Then discoveries there, and then machine learning. There's just several areas you can say countless. Now currently I'm working on quantum finance. I'm writing quantum algorithm for trading market where future option is going on. So how we can predict with more accuracy. So currently I'm working on that one, quantum finance. So if you are interested in quantum finance, please contact on my email, which is mentioned earlier. So there is several areas here that quantum computing is actually doing great job. So here, when we start with quantum, the very basic things is we need to understand this qubit. So this is similar kind of like bit only, but there is some difference. So difference is what is made is that we can notation. One is we used to write in terms of notation, which is direct notation, and this 0 bit we used to write like this. Direct notation, 1 bit we used to like this. The main importance and main difference from classical bit to quantum bit is that superposition. So superposition, we used to write the linear combination of states, which is, let's say, this is our qubit phi. Phi can be written in superposition state is alpha 0 plus beta 1, where alpha and beta are complex number, where we can write here phi equal to cos theta 0 plus e to the power I phi sin theta by 2 1. So if you take this coefficient of 0 and 1 and square it and add it, you will get 0. Like alpha square plus beta square should be 1. And here number theta and phi define the point and the unit dimension is there. You will see this equation again repeated times because we are going to use this one and explain several multiple things. Here the superposition state is to understand in better ways that suppose you have a coin and that has a probability of head and tail. There's two probabilities there. So if I ask that what is the probability of head once you toss it, and you can say after measuring that this much probability is for head, this much probability is for tail. And if I ask that, and based on that you can write head and tail. But if I ask that if you toss a coin, what is the probability you can write in air when it's in air? So you cannot write. You cannot write head, you cannot write tail. So in classically, but in quantum mechanically you can write in terms of superposition. So head, you can put it here head, probability of head plus probability of tail. So this is also one way of understanding this superposition, which is something different from qubit. We'll discuss this on how we are going to, some example of this qubit. So in microscopic level, and we can see that nucleus has, let's say this is our ground state, and this outer one is excited state. So when electron is ground state, we can write as this 0-bit state, 0-bit information. When this is in excited state, we can write here one qubit state. Now there is several other ways representing this plus is 1 by root 2 1 1. So we just focus on this one. 0-bit information we used to write like 1 and 0, and that is in matrix form, to class 1 matrix form. 1 bit is 0 and 1, like that. So this is how we used to rewrite qubit in terms of matrix. So remember, this from 0 is 1 0. Because we are going to use this qubit, and we are going to do some sort of computing stuff, so you have to remember this thing. So that is for one qubit. Here, this is for 1 qubit. If you want to write 2 qubits mathematically, so here 2 qubit this is we used to write in terms of tensor product. So let's say this is q1 is 1 qubit, q2 is 2 qubits. So if you want to write the combined state, then you have to write in tensor product. Let's say this is phi is final outcome, so q1 tensor q2. For example, q1 is, let's say, 0-bit information, q2 is 1-bit information, so psi equal to 0 tensor product 1, and this representation is like 0 1, 0 and 1. This is going to be like this. I will show you that how we can write this one. So 0 0 we can write in terms of matrix from 1 0 0 0. 0 1 is 0 1 0 1, like that. So similar way, if you do the matrix multiplication in terms of tensor products, we can see. In coming slide is there also, I will explain this one. For 3 qubit, we can write here its class 4 matrix 0 0 0 is equal to 1 0 0 0, like this. For 0 0 1, this is 8 combination 2 power 3. 3 qubit 2 power 3 is 8 combination. So like that we can write qubit in terms of for 3 qubit 0 0 0 0 0 1 0 1 0 0 1 1. These are the representation of 3 qubits. Now this qubit we can visualize on block sphere. Block sphere is just to representation of qubit. So here we have seen that our qubit phi equal to cos theta by 2 in earlier slide, 0 plus e power I phi sin theta by 2 1. So we have seen here. So if you look at this, this is our block sphere. You consider this one. So let's say this has this is in 3 dimensions: x-axis, y-axis, and z-axis. So this is very much useful to visualize things and help to understand superposition, phase shift, and gate operation. So all these things is easily to we can see on block sphere. So for example, let's say you remember this formula here. So let's say this alpha psi equal to alpha 0 plus beta 1. So alpha and beta is a complex number. We have mentioned earlier that alpha square plus beta square should be 1. So if you alpha equal to cos theta by 2, beta equal to e power I phi sin theta by 2, and if you square this, take mod here, mod alpha square plus mod beta square, that is cos theta by 2 square plus I phi sin theta by 2 square. So this, if you take the conjugate of this one, so e power I phi minus e power I phi, so it will be cancelled, becomes 0, e power 0 is 1. Here sin square theta by 2 is left, so cos square theta by 2 plus sin square theta by 2, as per assumption we know that cos square theta plus sin square theta equal to 1. So this should be follow this assumption. Here this phi equal to cos theta by 2 plus e to power I phi sin theta by 2, 1, qubit 1. Now let's say theta is equal to 0. If you put here theta is theta equal to 0, so this is become cos 0 and this is become sin 0. So phi is here. So theta equal to 0, so it become cos 0, 0 bit, e to power I phi, sin theta is 0, so this is sin theta, sin 0 is going to be 0, so no matter what is phi is going to be 0, so you are getting here cos theta 0, cos theta 0 is 1, so you are getting here 0 between function. So when theta is 0, representing your z axis. So opposite of this is going to represent your 1 between function. Means if I put theta equal to pi, so this is theta is pi, and phi equal to 0. So in this case, if I put theta equal to pi, so it's become cos pi by 2 plus e to power pi is 0, so e to power 0 is 1, and sin pi by 2 is 1, so we are going to get 1 between. So this is opposite of this. Earlier this is z axis, this is less than north pole, this is south pole. So we are getting here when theta equal to pi and phi equal to 0, we are getting here 1 between function. So this is what the way we are representing. You will see here this superposition state also. So when theta equal to pi by 2, phi equal to 0, so in this case cos pi by 4 e to power 0 and sin pi by 4, so it's become 0 plus 1 by root 2. So this represents actually your superposition state. So this will go, this theta is pi by 2, so this is, all these axes are, making 90 degree to each other, so pi by 2 here, so this z axis is not x axis become your superposition state. Of this one is a superposition of -1, so we can see here this is 0, 1 bit is here,
okay, bye.
Right. So this is how we can use our qubit on here. So I hope this is now seen here qubit, what is qubit, how to represent qubit. Then now we are going towards to discuss. We know that gate working. If I this AND gate, so AND gate input is get information so here this quantum gate is going to be different from the main difference is this is about reversibility. What in fact 1 classical operation, okay. And that's why this is the biggest problem and for big okay, quantum process. See this quantum gate is different. Of course, this is quantum gate similar to class have the degenerate output. The original input which can be derived from their output. There must be reversal. This is the deterministic computation from quantum computer only if it is reversible. Like it has been found that computation. 1973 they have mentioned this one. So here we will see this some quantum gate. So first I am talking about this Hadamard gate. This is a very simplest gate involves one qubit, and here we can write here, this is, suppose you have a 0 bit information here, and if you want to operate Hadamard operation, then it will make a superposition state. How this is going to work, we'll see. If you 1 bit information is there, then after applying this Hadamard, you will get superposition here 1 by root 2, 0 bit minus 1 bit. So here, how this is working? We know that matrix form representation of qubit 0 and 1. We have seen for 0 is 1 0 two-class matrix. For 1, it's a 0 1. So let's say now I'm talking about this 0 bit information. 0 bit can be written in terms of 1 0 in matrix form, two-class matrix, and this is Hadamard. So once you apply this on this this matrix, so the matrix for Hadamard is this 1 by root 2, 1 by root 2. This is 2 plus 2 matrix, 1 by root 2, or minus 1 by root 2. And this is, so here actually when we are operating this is in quantum computing, so we used to write from right to left. So this qubit operate on Hadamard, so we will write first Hadamard and then this qubit. So this is 2 cross 2 matrix, this is 2 cross 1 matrix, the final 2 cross 1 matrix you are going to get. So how this is going to work? If you apply this one, so 1 by root 2 into 1 plus 1 by root 2 into 0, like that, 2 cross 2 matrix operation. And so if you solve this one, you are going to get 1 by root 2, 1 by root 2, so you can take the common 1 by root 2, so you will get here 1, 1, 1 and 1. This is how this superposition state is represented. So this is how this Hadamard gate is working. And we used to denote by H. We'll see this in quantum circuit. Like the same way, I'm going to discuss about this quantum control NOT gate. So in this operation, control NOT gate is here. There is 2 input is here. So this is value for 2 qubits. So we are taking this one as a control, and this is the target. Am I audible?
Yeah,
Hello?
yes, sir. Yes.
Okay. So here this control gate is here. We have a control, we have a target. So how this is working is that if control is 1, then it will flip this target bit, otherwise it will remain same. So let's say here our input is A and B. So corresponding this outcome is A prime, P prime. So when input is target is 0 and control is 0, so what happens is that it's not going to change the A bit. So it will remain the same, 0, 0. When control is 1 and input is 1, it will flip this input bit. So you are getting here 1 and control remains the same. Here 0 and 1, so it's not going to change here. So 1 and 0. Here this is 1, control is 1, so it's going to change. So this flip this 0 bit and 1. So this is how this control NOT gate, quantum gate, control NOT gate is working. There is another gate. We can do similar way how we have seen here in matrix form. We can write the matrix for control NOT also and work on this one. So there is a 4 cross 4 matrix is there for control NOT gate, and because this is working on 2 qubits, so for 2 qubits we need 4 cross 1 representation of qubits. That's already we have seen here. If you remember, this is 2 qubits, is 4 cross 1 matrix, and C NOT gate is also 4 cross 4 matrix. Similar way, we have another gate which is C NOT gate. We also used to call Toffoli gate. So here, this has a 2 control. We are taking there is 3 qubits is there. So 2 qubits we are taking as a control 1 and target. So B and C is, let's say, control 1 and control 2, and this is target. The condition is that when both the control is 1, then only it will flip this target. Rest of the part it will remain the same. So here, if you look at this A and B, say B and C. So here you can see this both control is 1. So 0 is input, now it's become 1. And here also both are 1, 1. So it will flip this. So 1 becomes 0. And rest of the cases it's not going to change. Whatever input is there, you are getting the same output. Quantum gate is a reversal gate. That's what I had mentioned earlier. You can see here also, if you take this one, this portion as the input, and this is outcome. So if this portion, so this B prime, C prime as a control 1 and control 2, and this is input. So in this case, this B prime and C prime is whenever is 1, 1, 1, and this is 1, it will flip, it will become 0. So whatever input is there, you are getting here outcome, whatever output is there, if you pass through this CC NAND gate, you are getting. So this is a reversible gate, which is this classical gate doesn't work like this. So I hope this gate part is clear. I have discussed three quantum gates. Apart from that, there is a multi-gate which is belongs to quantum gate. So identity gate is there, Pauli X, Y, and Z gate is there. Hadamard already I have discussed. CC NAT is. So for that, this is the matrix for identity matrix for Pauli, and this is for Hadamard. This is for control NAT. This is control NAT. And how we are, operating this one. So we have seen that here Hadamard operating on 0 is giving superposition, on 1 is giving superposition. Here CNAT gate we have seen is that whenever control, this one is control, this is target, so whenever this is 1, it will flip here 1 1, and this is here 1 also, so it is flip here 0. So like this CC NAT gate is also, if you are taking here to control, this first one, second one is to control, this is target. So wherever double one is there, this 1 and 1, here 1 1 is there, so it will flip this 0, it will become 1. When T 1 1 0 1 1, it become 1 1 0, like that. So it's very simple. I hope it's understandable. If you still have a doubt, I'm ready to discuss after this presentation. So now the next part is that entanglement. So here, when we talk about this entanglement, so what is entanglement? Entanglement is it's a kind of magic. Why I'm calling it a magic? Because we have seen in Indian movies, I'm taking the difference from that when you have seen in movies about the twin. So there is two brother or two sister. We can take an example. Let's say two brother is there. One is sitting in Mumbai, one is sitting in Hyderabad, and because they are twin, if you disturb to one fellow here in Hyderabad, and if you measure they are in Mumbai, then we have seen means it get that fellow is also get disturbed. So means entanglement is here that two particles are there, which is separated with respect, no matter how long they are distance is there, but that is not going to matter. But if you measure one property, you will come to know the other fellow or other object property, that's what it is. So they are connected with magically. That's why I am calling this is magically. They are connected magically in irrespective of distance. So if you measure this person here, you will know that what is this person is there, or what is this object is there. If you measure this object, you will come to know that what is this object. So one is sitting in India, one is sitting in Australia, even though no issue. If you measure here in India, you can know that what is there in Australia. So this is the kind of magic, and they are not related to distances. Whatever distance is there. So for that, how this quantum entanglement is generated mathematically, I'm going to stop here. So we have for entanglement, we need at least minimum 2 qubit, 2 particles. So here we are taking a 2 qubit, 1 and 2. So we are going to make this entanglement here. So first we pass through the Hadamard. So here we are going to get superposition. We have seen in earlier slide. Once this pass 0 bit, we can get this Hadamard superposition here. And after this passing through this CNAT gate, so once you pass through the CNAT gate, this is going to be create entanglement. So this is the mathematical way to create this entanglement. So here you can see this one is that 1 by root 2. This is Hadamard gate. After this passing through this, we are getting this entangled state here. So there is a 4 major entanglement. We used to call them states: 0 0, 1 1, like that. There is a 4 possible combination is there. We'll discuss this one. So how this is going to work? That this Hadamard state and 0 bit. So we know that Hadamard operation in 2 × 2 matrix. 1, 1, 1 minus 1, and 1 by root 2 is common. And 0 bit information is to write 1 and 0. So if you multiply this matrix, you are going to get 1 by root 2, 1, 1. Okay, this can be written here 1 by root 2, 1, 0 plus 0, 1. This we can be right here 1 by root 2, 0 plus 1. This is what is there. So once we pass through this CNOT gate, so CNOT gate is this is what happening is that 0 bit is there and your superposition state is there. So here if you pass through this one, so 0 0 and 1 here 1 0. So here if you pass through this is a control 1. So 0 is passed through this one, so it will flip this one. So you are getting here 1 1. So once you pass this, so this is your entangled state. This is equivalent. This is the way that we can generate this quantum entanglement mathematically. And if you want to generate physical mode, so of course there are several methods. You can use Venus splitter. I work on this one, or you can use Vivio crystal. I have my paper is also published on entanglement, which is generated by Venus splitter. But distance is very short. We can use Vivio crystal. Is there take from strong electric field, I mean laser is there, and pass through this to entangle photon is there. So there's a multiple methods there to generate entanglement, and based on that, your requirement, your distance, and all, you can use those entanglement for different purposes. So this is how this entanglement is generated. Now next part is quantum teleportation. So we are going to use this entanglement property for quantum teleportation. So quantum teleportation is it's a kind of method because in quantum mechanics, due to no cloning theorem, we cannot make a copy of any state. So if you want to transfer quantum state from one place to other place, so since you cannot make a copy, so quantum teleportation helps to generate similar kind of state from one place to other place. We will see this how this is going to work. So the requirement is that tangle pair, that's what I already have discussed. Bell state measurement, classical communication is also needed. Once we measure this, do the Bell measurement, then whatever outcome is there, and then accordingly we'll apply this gate, and we'll get the actual information. So here, let's say we have some initial state, let's say 5. I want to transfer, let's say there are two people are there. In communication term we used to call Alice and Bob. You can call some other name also, there is no issue. So Alice is, she wanted to send some information, some quantum information to Bob. So using this quantum teleportation, let's say some initial information is there 5. We wanted to transmit to Bob and to get the exact information. So how this is going to happen? So for that we have to generate for entangled state. EPR we used to call this EPR source, which is generated this entangled pair. So first we generate this entangled pair. So once we generate this entangled pair, one entangle is goes to Alice, one is goes to Bob. Now Alice will do the measurement, Bell state measurement here with this and then quantum state to Bob and apply that this into the communication speed up right kind of communication. So going to vary based on see in circuit also how we can write this quantum teleportation. This is out here. So quantum circuit we have this quantum see quantum state is the initial state and two are entangled state. So 3 are there. So let's say 3 are there. So this is let's say this first and second is belongs to Alice, and third one belongs to Bob. So these Alice and Bob initial stage, they are in entangled state, and this is phi. That is what we wanted to send to Bob. So Bob will do here some operation here, do this well measurement, and based on this measurement outcome, apply this matrix. Whatever gate is there, a required gate, and after applying this one, you will get exactly this psi state, whatever initial state is there. Bob also has the same common state here. So this is how this quantum circuit is look like in IBM machine, IBM composer. You can see. I'll show you also here. So what is happening? So this qubit is there. So qubit Q0, Q1, Q2. So Q0, Q1 belongs to Alice, Q2 belongs to Bob. First is that they are going to entanglement. So entanglement, we have seen that here Hadamard and CNOT gate. So we have here Hadamard and CNOT gate, and this is the phase shifter that the information comes here. So so this is not playing much, but this is just for representation. So we generate here entanglement and do some bell measurement here, and based on this bell measurement, it's a 0 0 or 0 1 or 1 0. Based on that, we are applying here matrix. It's with RZ, RX, X, Y matrix, Z matrix. So based on this classical information, we are applying here. So accordingly, we are getting here the same information what we are sending here. So we are getting here. We'll see that one on IBM quantum machine also. So I wanted to first discuss the mathematical term, then I'll bring you to IBM quantum computing cloud machine. So in this one, for quantum teleportation, I have taken this some initial state, some generic state, psi equal to alpha 0 plus beta 1. Why I am taking this one? Because already from the beginning I am discussing about this one, alpha 0 plus beta 1. So this is we need to first clear the Bell state entanglement. So let's say beta 0 is we are creating here Q1, Q2 as a entangled state 0 0 and 1 1 by root 2. Then once we do this measurement here, so based on X and Z matrix, so probably X matrix is what is doing if you operate X on phi, this is phi, so it will flip this beta and alpha, so beta 0 plus alpha 1, and if it's Z matrix, so if it will change the sign here, and you can do this using gate operation or matrix operation. This is how we used to write the psi and X. X is also to pass to matrix, so we can see some slides. So here we have seen this Hadamard operation operated on zeros, giving entanglement, operated on this, getting this one. We already have discussed that we used to write here 1 0 0 1, and how we are writing 2 qubit is that 1 and this is 1, this is 0, this is 1. So 0 is used to write 1 0, so 1 and 0, and 1 is used to write 0 1. So 0 1. This because we are used to write in tensor product. So 0 1. So if you multiply this one, you are going to get 0 0. Like that, you have 0 0 information, 0 1 0 information, and 1 1 information. So this is tensor product. So tensor product actually follow the associative rule that does not commute. This one already have discussed here. So at the beginning we had taken phi here. So once we do this bell measurement here, then what this is phi naught, phi 0 becomes phi 0 equal to bell measurement and this phi for initial state. So if you put this beta 0 value, so phi 0 equal to phi we used to write alpha 0 plus beta, and entanglement is beta 0 plus 1 1 by root 2. So if you do the multiplication here, so alpha 0 0 0 plus 1 1, because and one is beta 1 0 0 plus 1 1. So here This first two qubits, consider that this is belongs to Alice and last one is belongs to Bob. So after this one, we apply here the C-NOT gate. This is phi 0, then phi 1 is after C-NOT gate. So once we apply here C-NOT gate, okay, C-NOT gate here, after then it will flip this Q1 when Q0 is 1. So Q0 is 1. So Q0 is this one, Q0 is this one. Okay, so because L is 1. So alpha 0 it will remain same because here control is 0. So 0 plus 1 1 plus beta is 1. So it's going to change here this 1. So 1 is going to change this one become 1 0 and this is 0 1. So after that you have to apply Hadamard gate. So that is how we know that how Hadamard is working. So apply this psi 2. If you apply here psi 2 Hadamard, then what will happen is that this information is there and Hadamard is 0 plus 1 bit information. So if you look at here, this alpha 0 0 0 alpha 0 plus 1, this is alpha 0 plus 1 and then 0 0 because this is going to be 0 plus 1. You apply this one and this Hadamard, so it's going to be 0 0 and this is 0 0 plus 1. Same here beta is 1, so it's 0 minus 1 and here 1 0 plus 0 1 after this Hadamard. So this state can be written by using associative law. Here alpha 0 plus 1 beta 0 minus 1. So if you look at the associative law, we can write this one 0 0 alpha 0 plus beta 1 0 1 alpha 1 plus beta 0 like 1 0. So there's a 4 combination 0 0 0 1 1 0 and 1 1. So how we used to write here this, let's say for example this is 0 alpha 0 plus beta 0 1. So this by using associative property we can write here 0 0 alpha 0 plus 0 0 beta 1. So this is what happened here. 0 we have taken 0 0 from this equation. So rewritten. So 0 0 alpha 0 plus beta 1. 0 0 alpha 0. This is how we used to write. So here if Bell measurement is saying 0 0, then no need to do anything. If it's saying 1 0, okay, then we have to apply this Pauli X matrix, and if 1 0 is there, then Pauli Z matrix. If then we need to apply Pauli X and Pauli Z matrix. So now I'll take you to iron. This is very I made this one, so I'll tell you here. So how this is working is that this is first we have created movement here between Alice and Bob, okay, and this is state, and then we put here phase shifter here, and this is NOT gate and Hadamard, and this is Bell measurement here, and to that if I put here, let's say 0 with information here, so whatever it's here, this is take some time. So yeah, we are getting the same here. And Hadamard. Here Hadamard is you can see here it's a superposition state. So here superposition state is written like this. So this Bob also has the same state here. So this is how you can write this on quantum. This is so quantum.cloud.com. You can go. one.
Sir, hello? Hello? Sir, we can't able to hear your voice. Hello, sir?
Hello.
Yeah, okay, sir.
Okay. So please just tell me what I'm supposed to start.
Yeah, okay, you can start now.
Yes.
Okay.
Can
Hello? Hello? Hello?
yes, I'm audible.
Yeah, yes, sir.
Okay. So
Hello?
yes.
Okay, sir. Now you can share the screen?
Yeah.
Okay.
Can you?
Yeah, okay.
Fine.
Yeah, okay, sir. You can start.
Okay. So I was talking about this. I'm talking about this. Is that how to make this quantum circuit, and in fact I have shown out. So this is the circuit. Okay, so this one. So this is how it's to write circuit and anaconda just skip and then Soorat. This is Qiskit and that is code of a quantum uh, that already we have seen that quantum circuit how, and this is the Qiskit code for this quantum teleportation is that how to create this one. So first create this entanglement, then Bell measurement, and then condition correlation. And here I just wanted to show you one more thing here. Right? This is we have circuit here. So this is what to keep Qiskit out. Just simply go to here and copy the code. No need to write the code, entire thing, and you put it in your Jupyter note, it will work. Okay, so I'm going to wrap up this one. So I have seen this. So nowadays in the real world there's a multiple companies where you can access this quantum computer. This IBM experience is there. Google has IonQ, Reggie, but biggest challenges with this quantum computer is decoherence and gate fidelity and error correction. So there's a lot of opportunity in this area. If you're working, you can directly get a chance to work with companies. So decoherence, gate fidelity, and error correction. And there is some common pitfall and myth. Myth is that quantum computers are just faster computers. It's not like that. They can replace classical computer. Also, it's not like that. They are ready for everyday use. No, this is not going to be easy. It's very expensive and it requires a lot of things. So it's not that easy. Okay. And reality is that, of course, it is speed and problem should be specific. It's not for simple mathematical 2 plus 2 or 5 plus 3. This is not for quantum computer, of course. And this is a complement for classical computer. It's not going to replace. And of course, the biggest problem is still noisy intermediate scale state in Skira. So yeah, this is what my talk so far. And if you have any question, I'm ready to answer it. Sure.
Yeah, sure. So first of all, thank you so much for this wonderful session, sir. So I have some questions here. So shall I ask those questions now?
Yes, yes. Please.
Okay, great. So my first question, how is quantum computing expected to outperform classical computers in solving real-world problems?
Okay, so the answer now, or you have to, again, you have the same question, I mean, another question. Should I answer this first?
Mm-hmm.
Okay, so when we are talking about everyday, so I have mentioned in the beginning that this is, see, most of the problem which is solved by classical computation, but this is for microscopic level problem. When you have huge amount of
Hello, sir.
so I'm really sorry for this interruption.
Okay, it's okay, sir.
I don't know why.
Okay. So that's my next
So,
question.
yes.
Yeah, okay. So what are the current limitations in building large-scale quantum circuits?
No, there's no limitation. No,
Oh,
not a open free
okay.
quantum circuit you want to make. I mean that is for your requirement, right? What is your requirement? How much information you want to proceed with this? Okay, how complex is your information? So I
Okay.
think this, of course, if you go for, nowadays these companies are also offering I will give it free. And if you are going to use some, there is some limitation in there. So if you are going to use more than that, of course, you have to pay little amount. It's not very much. Okay, so
Okay,
there's
okay.
no issue. You can make it.
Okay.
Yes.
Okay. Thank you, sir. Sir, how soon can we expect quantum computing to be used in industries like healthcare or finance?
Ah, the thing is that this is kind of lack of awareness, I can say, or people are not, of course, it's not that easy and straightforward like classical computer that we are used to. So once we are coming up with some courses, meetings, presentation, and all, and it's going to be uh, come to some people and start thinking about this. This is going to be easy. Quantum is not, of course, I can mention here because I have spent so much time learning this quantum mechanics and quantum related problems. Like from a PhD onwards, so it's like uh, 15, 16 years. So it's not that easy, but of course, nowadays we are trying to build up in such a way that it will be very useful for very common people to do this complex analysis part.
Okay, okay. Thank you, sir. What role do error correction techniques play in the future of reliable quantum computing?
The big company is this is very it become noisy and all. So this quantum error correction is a kind of open area. People are so many companies have a lot of vacancy in working towards quantum error correction. So this is of course this decoherence and quantum error correction is one of the biggest problem with this quantum computer. So yeah, it's open and people are working to live this and come up with better quantum error correction code, and if there's some error is there, so you can easily solve it.
Okay. So, how can students and beginners start building hands-on experience with quantum tools like Qiskit?
Yeah, that's what I have discussed about this presentation. So please go through this presentation. I think you have recorded. Just look at this recorded session, and this is the very basic. I have talked about very basic this qubit, quantum gate, and how to make the circuit on IBM quantum machine also. So this is so that we can get all the information in one form.
Yeah, yeah, okay. So some students only asking that same doubt. Okay. So, okay, sir. So, thank you for the useful answers. They have been really helpful in clarifying the topic. I hope the participants were able to follow along and understand the key points shared. So, your insights have certainly added value to the session. So, Dr. Ram Soorat, on behalf of everyone at the Mastering Up International Conference Series 2025 to 2026, we extend our heartfelt gratitude for your time, presence, and the incredible insights you have shared with us today. Your session on getting started with quantum computing from qubits to circuits was not only enlightening but truly inspiring. You have taken a complex topic and made it accessible and exciting for all of us. So, thank you for that. Your journey from deep academic research in quantum optics to real world applications in cryptography and innovation leadership has left a strong impression on every participant here. We especially appreciate the way you encouraged curiosity, simplified the key concepts, and opened up future possibilities in this evolving domain. It's voices like yours that motivate young minds to think beyond boundaries and explore the unknown. So, once again, thank you, Dr. Soorat, for being with us and sharing your expertise with such clarity and passion. We look forward to many more opportunities to learn from you in the future. So, wishing continued success in all your academic and professional endeavors. So, thank you, sir. Thank you so much.
Thank you.
Sure,
Thank you.
sir.
Thanks a lot.
And we will share the certification and memento within some time. Okay, sir?
Okay, thank you.
Yeah, great. Thank you, sir. Thank you
Thanks.
so much.
Thanks a lot.
Take care. Bye bye.
Bye.